Hello, my name is Srđan Kitić of Orange Labs, and I will present joint work with my colleague Jérôme Daniel on the new spatial imprint that we've termed Generalized Time-domain Velocity Vector. I will first discuss the motivation for this work, which is rooted in the so-called eco-aware acoustic signal processing. Then we will recall some concepts related to spatial audio and ambisonics. Then I will discuss our previous work on time-domain velocity vector and discuss its limitations. This will motivate the introduction of a new, generalized version of the velocity vector, whose performance is evaluated through acoustic simulation experiments. The presentation will end with some conclusions and perspectives. We are inspired and very excited by the possibilities of what we call eco-aware acoustic signal processing. In brief, the idea is to infer the acoustic environment in terms of its geometric and acoustic properties and to exploit this knowledge for various use cases. Some of the notable ones are room geometry estimation, source localization around soundproof obstacles, sound enhancement by rake receivers, robot navigation, and scene-aware rendering for virtual and augmented reality applications. Obviously, such applications require estimating the spatial and acoustic properties of the environment. Numerous methods for extracting such information have been proposed in the past, for instance, using pre-recorded room impulse responses or multimodal data. Our aim is to infer as much as possible using only the audio modality in a passive mode and without knowing the source signal or its position a priori. We use the Ambisonic spatial audio format, which is very well suited for acquisition, playback, and rendering of three-dimensional sound scenes. Ambisonic encoding is based on linear projection of the recording multichannel microphone signals onto the basis formed by real spherical harmonics functions. The decoding process is also linear, and it is tailored to the type of the output system. Therefore, Ambisonic's representations is, in a certain sense, agnostic with respect to the type of the recording array and the loudspeaker layout. In practice, spherical harmonics decomposition is truncated, meaning that only the coefficients up to some maximal order are retained. First order ambisonics, or FOA, keeps only 4 channels. Alternatively, higher order ambisonic signals have more than 4 channels. Let's recall the basics of ambisonic sound capture, which will allow us to make connections to some well-known concepts in acoustic signal processing. Let's start by discussing the simple scenario where an FOA microphone records the sound coming from a single source in free field. First FOA channel, often labeled by the letter W, is omnidirectional. The remaining 3 channels, X, Y, and Z, are akin to figure-of-8 directed microphones, aligned with Cartesian coordinate axes. Ambisonic channels are assumed to be in phase, meaning that every plane wave is simultaneously registered by each channel. In the 3-field case, all channels record an attenuated and delayed source signal. This captured signal S at the microphone W is multiplied by a constant. Here the constant is 1. Each directional channel, X, Y, and Z, multiplies the signal S by a Cartesian coordinate of the unit vector U pointing towards the source. And clearly, if we divide these 3 channels by W, we get rid of the source signal, and what is left is the source's DOA vector. This quantity is known as the velocity vector, and its real part is also known as pseudo-intensity in the literature. Velocity vector is complex valued in general, but it, as shown here, it becomes real valued and unitary in the plane wave case. In reverberant environments, the velocity vector analysis is more intricate. For simplicity, let's consider the setting where only the direct path and few spectral reflections are recorded. On this figure here, we can see the norm of the multi-channel ambisonic spatial room impulse response as a function of time. Each plane wave is assumed to arrive at a different time instant at the microphone array. In frequency domain, each plane wave vector is weighted by the complex gain gamma n, which encodes the relative delay and attenuation between the given wavefront and the direct path. Hence, the ambisonic channels record a sum of different plane waves, each weighted by the source signal S and modulated by the corresponding factor gamma n. Obviously, dividing the channels x, y, and z by w still produces a quantity that is free from the source contribution S, but it is no longer aligned with the DOA vector. Here we denote DOA by U0. We've termed this quantity the frequency domain velocity vector, or relative transfer function in spherical harmonics domain. For higher order ambisonics, frequency domain velocity vector is obtained by dividing each HOA channel by the W. The temporal representation of frequency domain velocity vector is obviously the time domain velocity vector, or the relative impulse response in spherical harmonics domain. If we plot its norm against the norm of the corresponding spatial room impulse response, we observe an interesting sparse pattern where some of the TDVV peaks correspond to the peaks of the room impulse response. So, how can we interpret this quantity? To analyze the time domain velocity vector, we turn again to its frequency domain counterpart, the FDVV. Under the assumption that the magnitude of all gamma n factors is lower than 1, we first develop the FDVV denominator into Taylor and particularly geometric series. After some manipulations, we can isolate the direct path wavefront, the power sums involving only the difference between the direct path and dish reflection, and the remainder which involves the interferences among reflections themselves. Taking the inverse Fourier transform leads to a series where we can easily identify the DOA vector U0 at the delay equals 0. The remaining peaks correspond to the differences between U0 and the reflections UN, which periodically reappear with decaying magnitudes. The first peak of each such subseries is found at the time delay equal to the relative delay between the direct path and the corresponding reflection. So, in such favorable conditions, the TDVV has an interpretable structure from which we can extract the DOA, reflection directions, and their associated delays. Right, but let's discuss what are these favorable conditions. Now we are discussing FDVV and TDVV from the filtering point of view. In frequency domain, velocity vector corresponds to the ratio of the transfer function of each channel and the transfer function of the channel W. Analogously, in time domain, velocity vector is the convolution of the impulse response of each channel and the inverse of the impulse response of the channel W. Hence, TDVV is actually the multi-channel spatial room impulse response altered by the convolution with the filter HW inverse. There are two possible scenarios. If we are lucky, the cumulative strength of all reflections will be lower than the strength of the direct path, and the impulse response HW is a minimum phase filter. Hence, its inverse is also stable and causal, and the resulting TDVV is very similar to spatial room impulse response as discussed on the previous slide. If this is not the case, the impulse response HW is non-minimum phase, and its inverse will, in a certain sense, pollute the resulting TDVV, which is no longer causal, and it cannot be interpreted by the Taylor series. The conclusion is that the TDVV is interpretable only if its denominator, or the impulse response of the channel W, is a minimum phase filter. Unfortunately, this is rarely the case in real acoustic conditions. In this work, we propose a simple method to fix such a denominator. Instead of using the omnidirectional channel W as the reference, we can use a linear combination of all channels. This allows us to condition the reference such that it remains a minimum phase filter. The simplest idea would be to apply a fixed beamformer pointed roughly towards the direction of the source. The resulting generalized frequency domain velocity vector admits a very familiar expression, except that now each factor gamma n is also multiplied by the value beta n, which is the beamformer's response in the direction of the reflection un. The chances are that such weighting satisfies the Taylor series condition much more often. Its temporal counterpart, generalized time-domain velocity vector, has also a very familiar structure. We can again identify the direct path by evaluating GTVV at delay 0. However, due to the beamformer, the first peak of the series involving some reflection n is now almost aligned with the plane wave vector associated with the direction of arrival of this reflection. This will hold if the reflection is outside the main lobe of the beamformer, or in other words, if the reflection is sufficiently away from the DOA of the source. In practice, for real signals where the signal-to-noise ratio varies across frequencies, it is not feasible to compute the generalized velocity vector by simply evaluating the ratio between the channels and the beamformer. And instead, we propose to use an adaptation of a well-known stationarity-based least square estimator that involves power spectrums and cross correlations of all ambisonic channels. This video illustrates the behavior of the classical and generalized time-domain velocity vector for a moving sound source in simulated conditions and for the ambisonics of order 2. Clearly, GTVV is much more robust compared to TDVV, and it remains causal in most cases. For a numerical evaluation, we have simulated a shoebox room with low and moderate reverberation under mild noise. We compare the source localization accuracy of generalized and classical TDVV, as well as a classical beamforming based method for various ambisonic orders. In addition, we compare the performance of TDVV and GTVV in terms of the detection rate, localization accuracy, and delay estimation of the acoustic reflections. And in all cases, GTVV clearly outperforms other methods. This research was initiated by the need for appropriate tools to address eco-aware acoustic signal processing. We feel that this is a promising research avenue that may lead to disruptive technologies and use cases. We have concluded that the parameters inferred from classical relative impulse response in spherical harmonics domain are biased due to the fact that the omnidirectional impulse response is almost always non-minimum phase. We propose to address this by simply replacing the omnidirectional reference with a beamformer, which is termed then generalized TDVV or GTVV. GTVV may include HOA channels as well, and it has been shown that it offers much better stability and that it facilitates estimation of acoustic reflections. In future, we will focus on applications of GTVV, on improved regression, etc. And finally, if you are interested, as well as us, by the eco-aware signal processing, we warmly invite you to our upcoming session at UCIPCO 2022. Thank you very much for your attention.